Hello everyone. Today we will discuss one of the topic in discrete mathematics, especially in graph, which is directed graph. So let's just start with the first the definition. So a directed graph, or we can call it a digraph, consists of two sets, V and E, just like any other graph. But here, V, of course, the set of non-empty set of vertices, and E here is a set of directed edges. So the edge must have directions. Each edge here is an ordered pair of vertices. So the directed edge UV set to start at U and end at V. Then UV doesn't equal to VU. Then for an edge UV, then U is called the initial vertex of the edge, while V is the terminal vertex of the edge. If the initial vertex is the same as the terminal vertex, then we will have a loop. So for example here, we have loop A, loop C, and loop E. For the degrees of directed graphs, we have two definitions here. The first one is in degree and the second one is out degree. The in degree of vertex V here, denoted as this one, degree minus, is the number of edges which terminate at V. So for example, for P here, for vertex P, then there are two edges that terminate at V, so the in degree of P is 2. And then the out degree here, denoted as degree plus, is the number of edges with V as their initial vertex. So again, for vertex P, the out degree is 1 because there is only one edge that terminates that starts from P. So the out degree of P is 1. For a loop, then it contributes 1 to both the in degree and the out degree of the vertex. So for example here, for A, then this loop contributes to both the in degree, contributes 1 to the in degree and to the out degree. The number of edges of directed graphs can be counted based on the total in degree or out degree of the vertices in the graph. So we use this theorem. G here is a directed graph. Then the total number of E is the summation of the out degree of the in degree, of the in degree of V, in which V is an element in the set V, or it is also can be counted by the summation of the out degree of all vertex V in set V. For the connectedness in directed graphs, we have two definitions here. The first one is strongly connected. So a directed graph is strongly connected if there is a path from any from vertex A to B, and a path from B to A whenever A and B are vertices in the graph. So A and B are any vertices in the graph. An example of a strongly connected graph is this one, graph G, because here if you pick any two vertices as the initial and terminal vertex, then you can always find a path. So from A to B we have a path, from A to C we have also a path. From C to A we have a path, from D to B we also have a path here. So this is a strongly connected directed graph. The second one, directed graph, is weakly connected if there is a path between every two vertices in the underlying undirected graph, which is the undirected graph obtained by ignoring the direction of the edges of the directed graph. So in here, actually, we have, if we eliminate all the direction, then we will have an undirected graph, and the undirected graph is connected. Yeah, then that's weakly connected. So by default, actually strongly connected is also weakly connected. So because if we eliminate all the directions here, then the underlying undirected graph is also a connected graph. But we will have a better example here, graph G. Graph G here is not strongly connected because, for example, from A to T, then we do not have a path at all, because A is only a terminal vertex here. Yeah? There is no edge from A to any other vertex. So this is not strongly connected. But if we eliminate the direction here, then what we get is a connected undirected graph. That's why graph H here is weakly connected. Then related to strongly connected, we also have a component in the graph. It is a subgraph of a directed graph that are strongly connected but not contained in larger strongly connected subgraph. So it is a maximal strongly connected subgraph. It is called strongly connected component or strong components of G here. So here, if we find a maximal subgraph which is strongly connected, then that's strongly connected components. An example here, again, graph G. Graph G here has three strongly connected components. The first one is this one, yeah, BCT. So if you pick any two vertices, one as initial vertex and the other one as a terminal vertex, then we can always have a path here from P to C, from C to P, from C to T, from T to C, yeah? And then from T to P to T and T to P. So this is strongly connected components, and it cannot be extended, yeah? Because if we include, for example, E, then there is no path from E to any other component here. If we extend it to A, then there is no edge from A to any other vertex here. So we cannot extend it to either E or A. Yeah. So this is the maximal strongly component. And then for A, how about A? A here cannot be extended to any other component, to any other vertex as well, because A by itself, yeah, from A we cannot go to anywhere, yeah. So A is strongly connected by itself. The same also applied to E. Yeah? So from E we cannot go to any other. We can only go to A, yeah. But from A to E, there's no path. Yeah? So E is also strongly connected by itself. So there are three strongly connected components in graph H here. The first one is vertex A, then vertex E, and then subgraph consisting of the vertices B, C, and D. In a directed graph, there is this term, directed cycle. A directed cycle here is a path, yeah, in directed graph with positive length. Yeah, so the length must be positive. It cannot be zero, yeah. Positive length starts and ends at the same vertex. So this is an example of a directed cycle. Yeah. So using this cycle, we can start from any cycle or from any vertex back to itself. Yeah. For this four in these four vertices. Related to directed cycle, a directed graph which doesn't have a directed cycle is called directed acyclic graph, or DAG. DAG. So if we can see from this example, there's no way for us to form a directed cycle here. So this graph is called directed acyclic graph. Directed acyclic graph. It means that there is no directed cycle in the graph, in the directed graph. For a directed graph, we can have a transitive closure here. A digraph. It is a digraph G star, such that the vertices of G star are the same as the vertices of G, and G star has an edge UV whenever G has a directed path from U to V. So here, this is the original digraph G, and this is the transitive closure. Why? Because here, for example, we can have a path from this vertex, from this vertex to this vertex, using this path actually, this and then that. So as a transitive closure, then there is a directed path from this vertex to that vertex. The same also happens to this these two. There's a path from here to there via this path, this, and then that, and that, this one. So there is a directed an edge, directed path, or an edge from this vertex to this vertex. Actually, a directed graph can be formally considered as a binary relations on the same set. In this case, set A, because as you remember, we can also represent a relation using a graph, directed graph. So we can draw a digraph here geometrically by representing elements of A as vertices and directed edges that connects the vertices, just like how we represent A RP. It means that A related to P. So an element here is represented as a vertex, this one, and then the arrow or the arcs between a vertex to another vertex is represented as an edge. This is an example of relation. The relation here is divides on set of integers from 1 to 12. So, for example, there is an arc, an edge from 2 to 10 because 2 divides 10. There is an edge from 2 to 8 because 2 divides 8, and so on. Then there is a loop. For every vertex, there is a loop because a number divides itself. We can define new relations based on the paths on digraph R here. So if R is a digraph, then we can define at least two new relations here. The first relation is A R star P. It means that there is a path from A to P. So A is related to P if there is a path from A to P. And then there is also another relation here, AR plus P. It means that there is a path with positive length from A to P. So R star here is a path relation of R, while R plus here is a path relation with positive length of R. So in this case, R plus, the length of the path in R plus must be positive, not just, it cannot be zero. DAG can be considered as partial order. There's a lemma here. If D is an acyclic directed graph, then D plus is a strong partial order. A strong partial order means that there is no element that is related to itself. So there is no loop here. There is no loop in strong partial order. Yeah. So the relation T plus, which is this one. There is a path with positive length, from the two vertices in the graph. Then it will be a strong partial order. That applies when D is an undirected acyclic graph, or DAG. This is an example of strong partial order in a directed acyclic graph. So we have here, for example, this is a graph task in scheduling problem. If we want to wear we wear everything, then we start, for example, from the underwear, and then pants, and then pants, from pants then belt. But we can also in parallel doing this one, shirt, and then sweater, and then jacket. We can also in parallel doing this one, right sock, and then right shoe, or left sock and then left shoe. But if we can only wear our shoes and our jacket and our belt after we wear our pants. That's how we get dressed. Okay. Another one, topological sorting, actually related to the previous slide as well. Topological sorting for a DAG is a linear ordering of vertices such that for every directed edge UV, vertex U comes before V in the ordering. And it is not possible if the graph is not a DAG. So it must be a directed acyclic graph. If it has a cycle, then we cannot make a topological sorting. This is an example of topological sorting for this graph. So we can start from 5, and then 4, 5, 4, and then 2, and then 3, 1, and 0. If we pick any pair here of vertices, for example 5 and 2, 5 and 2, then as we can see here, 5 appears before 2, because 5 must be done before 2. Then 5 and 3 also the same. There's a path from 5 to 3. Then 5 is placed on left of 3. And then 4 to, not 4 maybe, 4 and 0. 4 and 0, 4 appears before 0. And then 2 and 1, 2 appears before 1. So this is an example of topological sorting. And the topological sorting for a graph is not unique. So we can also have another topological sorting like this. But we also need to follow this rule here. So in this rule, for every directed edge UV, vertex U comes before V, in the ordering. And then the first vertex in topological sorting is always a vertex with integrity as 0. In this case, a vertex with no incoming edges. So the first one should be 4 or 5, 5 or 4, because each of them has integrity 0. And that is also related to the definition of minimal element in a partial order. So topological sorting is easy to be built if we started from a minimal element. The minimal element here is the element in which there is no other element that is smaller than it. Yeah. So there are three minimal elements in this partial order. The first one is A, because A, there is no element which is smaller than E, than A. Remember that this is a hazard diagram. So the one that is placed here from A to C, for example, it means that A is smaller than C. So there is no element smaller than A, and then there is also no element smaller than P. Now, what about A? Now, we cannot compare P and A because there is no path from P to A or from A to P, and the same also applies for E. So there are three minimal elements here: P, A, and E. And if we want to make topological sorting, then we can build the topological sorting started from any of these minimal element. Yeah, related to partial ordering or poset here, we also make a chain. So a subset of, it is a subset of S, yeah, in which every two elements in C is comparable. So we can always compare two elements. That's a chain. A chain is a subset of S in which every two elements in C is comparable. And we also have this one, chain length. This is the most number of elements that are comparable in C. And chain here is called totally or linearly ordered set. So it's not a partial ordered set, yeah, like in poset. It is called a totally or linearly ordered set. An example of chain is a set of integers, because we always be able to compare any two integers. So set of integers is an example of a chain. Yeah, this is another example of a chain. This is the hazard diagram of a poset. There are 5 elements here: A, B, C, D, and E. We can have a chain here. For example, we have chain A, D, E. Yeah? This is a chain with rank 3. We can also have A, B, C, E. This is a chain of length 4. Yeah? 1, 2, 3, 4. Yeah. But ABD is not a chain. ABD here, because we cannot compare B and D. B and D are not comparable. So B and D, ABD here is not a chain. Yeah, we have chain and we have also anti-chain. In a poset, subset A of S is called anti-chain if there are no any A and B in which A less than or equals to B or B less than or equals to A. So in the anti-chain, then we cannot compare elements. There are examples of anti-chain in this hazard diagram. CD, yeah? CD. This is an anti-chain because we cannot compare C and D. And then BD is also an anti-chain. Yeah? And then by default, A is also an anti-chain. Okay. There is a theorem related to the number of chain and anti-chain. If S is a poset of set S and the longest chain in the poset is of length n, then S can be partitioned by n disjoint anti-chains. Yeah, so we have here this poset, and this is an example, and the longest chain here is 4, I think. Yeah, 1 2 3 4. Yeah, 1 2 3 4. Yeah, the longest one is this one, or this one is also the same. Yeah. It should be A here. So we can partition S here by 4 disjoint anti-chains. This is the 4 disjoint anti-chains. The first anti-chain is this one, A, B, C, D. Yeah? There's no connection between these 4 vertices, so this is an anti-chain. And then the second one is this one, DF. Yeah? Actually, you can also include E in this second anti-chain. Then the third one is GH, and then the fourth one is IG. So in every anti-chain here, we cannot compare, yeah, the elements. We cannot compare A and B, we cannot compare BC, we cannot compare EC, and so on. With regard to that one, there is a lemma here which is called Dilworth lemma. This is related to partial order. For all T, every partial order in a set with n elements must own either a chain which length is larger than T, or an anti-chain of size at least n divided by T. So in this case, for all T, of course T must be less than or equals to n. We can have a chain which length is larger than T, or an anti-chain of size at least n divided by T. Maybe it will be clear if we go to this example. Yeah? Consider this poset. There are 10 elements here. Just pick T equals to 2. Yeah? So in this case, there is a chain longer than 2, or an anti-chain of size at least 10 divided by 2 equals to 5. Yeah, it can be, one of them can be correct. So in this case, there is a chain of length larger than 2. We have ATGI. ATGI is a chain of length 5. Chain of length 4, sorry, 5. A chain of length 4. So for this case, when T equals to 2, then the first one is correct. There is a chain longer than 2. But there's no anti-chain of size at least 5. Yeah, in this case, we cannot find any, I think. 1, 2, 3, 4. I think the most, there are the size of, the maximum size of the chain is 4, I think. So it is not possible to have an anti-chain of size 5. Yeah? So the first one is the correct one in this case. Pick another one of T, yeah, T equals to 5. Then there is a chain longer than 5, or an anti-chain of size at least 10 divided by 5, which equals to 2. For this one, we cannot have a chain longer than 5, because the maximum length of the chain is 4. There is no chain longer than 5. But the second one is correct. Yeah. We have an anti-chain of size at least 10 divided by 2. In fact, we have an anti-chain of size 3. Yeah? For example, GHF. Yeah? GHF. Yeah? This is an anti-chain of size 3. And we can also have DEHF. Yeah? That's an anti-chain of size 4. Yeah? Okay, so this is the lemma, Dilworth's lemma. Okay, with regard to directed acyclic graph, can be used, like what we already previously in the previous slide, topological sorting. It can be used actually for parallel task scheduling, parallel task scheduling, like what I already mentioned before. We can, after we wear our pants, then we can have left shoe or right shoe or jacket, parallelly or paired. So we can start from this one, for example, and then parallelly we can also do this one, and then this one, and also this one. Vertices in any path of a partial order in DAG will form a chain. So this one form a chain, this also form a chain, this is also form a chain, any path will form a chain. The longest chain in a partial order is called critical path. The longest chain is called the critical path. We have several critical paths here, this one, and then this one, and then this one. And then the time to finish parallel task is equivalent to the length of the longest chain. Means that the time to finish parallel task is equivalent to the length of the critical path. In this case, we have DAG, and the longest path is 3. Sorry, it should be 3. It's 3. 1, 2, 3, 1, 2, 3. Sorry, it should be 4. 1, 2, 3, 4. Sorry, it should be 4. 1, 2, 3, 4. Actually, we have a chain of size of length 4. It should be placed a bit above here, so that we can see the chain. So this is the longest path. 1, 2, 3, 4. So the time to finish all tasks here in parallel is 4, because the length of the longest chain here is also 4. Okay, so that's how we use directed acyclic graph to model a scheduling problem. Okay, so that's it, I think. This is the references. Some of the slides are obtained from the book by Rosen, Discrete Mathematics and its Applications. Okay, I think that's it about directed graph. Thank you for watching, and I'll see you in the next topic of discrete mathematics.